And I'm Xizheng. I'm honored to be here to present our work, ZOOMSYNTH. And this is a joint work by Tsinghua University and Zhongguancun Laboratory. The title of the paper is Resolving Packets from Counters, Enabling Multi-Scale Network Traffic Super Resolution via Composable Large Traffic Model. And as we know, fine-grained traffic traces are highly valuable in network research. And we can categorize the use cases into two types. The first, some applications require packet-level traces, such as packet scheduling and congestion control evaluation, because they directly study each packet behaviors. And second, some tasks can work with coarse-grained data, but benefit from higher granularity, like anomaly detection and traffic classification and so on. In these cases, packet-level traces lead to better performance. But however, collecting fine-grained traffic is challenging. We can use TCP dump or some mirroring tools to capture packet-level data on devices, but in practice, the limited processing power and the storage capacity of devices make it hard to support such detailed capture. So as a result, fine-grained traces are really available at scale. While fine-grained traces are hard to collect, we observe that traffic counters are readily available in many network devices. It supports hardware counters. For example, we can easily obtain the number of packets and the total bytes for each second directly from the device. This leads to our research question. That is, can we reconstruct highly valuable traffic traces from highly available counters? And specifically from counter sequence, can we infer each packet's timestamp, length, and some basic header fields? And a similar cost-to-find task has seen great success in image domain known as image super resolution, ISR, and some modern ISR models can achieve high-quality generation at 8 times resolution. It benefits from extensive benchmarks and training data and some well-developed model architectures such as CLTMs and transformers. However, traffic super resolution is very different from ISR. First, the upscaling factor of TSR is much larger. In TSR, we may go from per microsecond counters to per packet traces, and this is 1,000 times upscaling. But ISR typically performs only 4 times or 8 times upscaling. And second, the data formats are different. TSR deals with time series data, while ISR operates on images. And finally, generality is harder in TSR because traffic patterns are very widely across networks. But image data, tends to share more structural similarity. So to address these challenges, we propose our system ZOOMSYNTH, a framework for traffic super resolution. And here is the overview. The input is a sequence of traffic counters, such as per second packet counts and byte counts. And it passes through a super resolution model, which infers fine-grained packet timing and length. Then, finer header assembler module adds basic packet headers and produce full packet level traces. And in addition, we want to generate packets, and we want the process is controllable. So For example, we may want to synthesize packets from that satisfy an ACL rule. So to achieve this, we introduce a clip module, which takes the rules as input and guides the generation process. And we also design some key modules to enhance ZOOMSYNTH, like a LoRa-based fine-tuning module, which allows for faster migration with minimal training, and a real-time generation module, and a multi-scale synthesis module enabling generation at different granularities. So let's start with the core module of our system, the Granular Traffic Transformer. We call it GTT. We design GTT because a simple transformer alone is not sufficient for the TSR task. We find that it tends to average out predictions and really struggles to capture extreme events. And to address these limitations, we enhance the transformer by adding a bio-LTM branch to learn extreme value patterns in traffic. And we borrow ideas from Zoom-to-net in designing our loss function. Specifically, in our case, the loss encourages two things. First, matching the real distribution use EMD and GXD. And second, ensuring that when reaggregated, the generated trace matches the original counter input. So together, these components form the GTT. The transformer predicts the best output Y based on temporal patterns, and the bio-LTM estimates an offset capturing extreme values. So the final output is Y plus Y offset, combining trend and extreme events. But however, we found that GTT is not sufficient as the final model for TSR, because we can find that when the super resolution ratio becomes too large, for example, upscaling from per second to per microsecond, there is a 1 million times upscaling, and GTT also fails. GTT's output again tends to average out. So to overcome this limitation, we extend GTT into a chain of GTTs. By doing this, we reduce the upscaling ratio of each GTT, and we also increase intermediate inputs and outputs, allowing the system to handle larger scale TSR tasks. However, this leads to later stage slowdown, and as we move closer to the final output, the GTT processing time grows because the input and output become too larger. So to address the slowdown, we further extend the GTT chain into a GTT tree. And this is our CLTM, we call a Composable Large Traffic Model. In the later stages, we use more parallel GTTs, enabling faster generation by distributing the processing load. And now, let's discuss our LoRa-based approach for faster migration. In general scenarios, we will pre-train CLTM on a general data set during this phase, or model parameters are trained. However, when deploying into a new scene, we need to fine-tune the model for, using a new data set for better performance. So to do so, we don't modify all parameters. Instead, similar to LoRa, we only train part of parameters. And here, we just fine-tune the last layer of the CLTM, because it most directly influences the output. And we also design a rule imperator to ensure the output that matches specific rules. For this, we use domain adaptation of the clip. We retrain the encoders and update the similarity matrix using rules and traces. This allows us to generate traffic that meets user-defined constraints, such as ACL rules or some filters. We trained ZOOMSYNTH using a total of 16 gigabytes data from 7 open source data sets, and the processes data converted into counters for training exists 1.7 terabytes. The final model has 1.8 billion parameters, and we'll come to measure and test it. And to evaluate ZOOMSYNTH, we compare it with net share, net diffusion, and zoom to net. We assess it across 4 key areas. The first, package generation performance using EMD and GSD to judge it. And second, we test if ZOOMSYNTH can achieve real-time generation. And the third, we want to see the performance on downstream tasks like anomaly detection, network measurement, and service recognition. And last, controlled generation of ZOOMSYNTH. The first, in packet generation performance, ZOOMSYNTH is comparable to net share, but outperforms our other baselines, specifically time steps and packet length generation. ZOOMSYNTH is 20.1% weaker than net share, but 48.4% stronger than others. And similar trends can be found in header field generation. And we also evaluate real-time generation. Even under 1 billion times upscaling, ZOOMSYNTH can generate all packets within 1 second. And this result is based on our open source data sets. And on 3 downstream tasks, ZOOMSYNTH also performs well in anomaly detection and service recognition. We train classifiers on generated traffic and test them on real data. ZOOMSYNTH achieves 27.2% improvement over net share in anomaly detection because of the robustness to outlier, and 9.8% improvement over net share in service recognition because of the better header generation. And in network measurement, we use sketch-based metrics to compare generated and original traffic. And in this task, ZOOMSYNTH is 22.3 weaker than net share because of inevitable distortion during upscaling, but still better than other baselines. And the last task, controlled generation. It also proves effective. The integrated clip consistently enhances rule adherence. It achieves 84% improvement under simple rules and 59% improvement under complex rules. And the last evaluation, we also evaluate the effectiveness of the LoRa-based approach compared to directly used pre-trained general model. LoRa helps us to improve generation performance across all fields, although it is not as strong as the full retraining with new thing data, but it reduced training times from days to hours. And finally, let's conclude our paper. We propose ZOOMSYNTH, the first system to reconstruct traffic traces from counters. And in it, we design GTT and assemble a tree-structured CLTM for real-time and high-quality synthesis. synthesis. We also introduced LoRa and Clip to ensure fast migration and controllable outputs. And ZOOMSYNTH achieves performance close to the SOTA method next year, but it generates packets from packets. But ZOOMSYNTH generates packets from counters, and ZOOMSYNTH successfully outperforms other baselines. That's all, thanks. And I'm happy to take any questions.